All right, got our recording on already. So here is Monday. This is our last week. We have 2 more chapters, okay? We have chapter 20, which is a means, okay? And I have about 30 slides on this. And what the themes we wanna look at is our selectivity and knowing the difference between our primary, secondary, and tertiary means, and how to synthesize specifically a primary, a secondary, or tertiary mean by using different routes, both oxidative and reductive, to get to our systems. And so that's what we're going to focus on today. And then we might get into chapter 21, which is organometallic mediated catalytic systems. And so it's basically taking the basis we learned from Grignard reactions and extending it to have these cyclic catalyst systems. And so we'll be looking at that by the end of the semester. And then we should have plenty of time to go over the 3 high points for each of the chapters that we'll be reviewing for our final on this week. Okay, so the first thing I want to do is do our administration. Everybody found the link? Well, at least how many of you? 30 of you have found the link, so that's great. Our homework for chapters 20 and 21, there's only 10 of each, okay? But it's still a total of 25 points. The keys here are that, looking at that selectivity of those reactions, and especially in 21, looking at the types of reactions we have. We have named reactions. Almost all the mechanisms are the same, but the names are different. And so that's what we'll focus on that. We'll have our final exam, and it is on Thursday from 2 to 4:30, okay? It will be administered through Proctorio. So I know some people had some internet problems. I think that all got fixed over the weekend. Even mine got fixed over the weekend. So I think that we should be good, assuming we don't have another thunderstorm roll in and blow us all out again. But that'll be hopefully not too bad. And again, I have on the thing chapters 11 through 21. It's actually chapters 12 through 21. So sorry about that. Don't want to scare anybody there. I will have some review sheets that kind of summarize some stuff from the first 11 chapters. For example, on the website and on Tracks as well as Canvas, there's a thing about nomenclature, okay? Go ahead and start reviewing that, because the difference between primary, secondary, tertiary is all there. And now that we know our highest priority groups, which is our carboxylic acid and carboxylic acid derivatives, that's how we're going to have to go back and rename everything. So I do have a thing that I'll give you as a review for that, but I will not be doing a activity this week. We're going to just do review, and then have the exam on Friday. That being said, that means our homework is due on Wednesday at midnight. So you'll have all day Thursday morning to review it. And again, it's only 10 questions on each, so you should be able to review up through chapter 19 before Thursday morning, and then be able to review chapters 20 and 21 that time. Okay, are there any questions about what's due this week or what we're going to handle this week? Okay, I'm not getting anything in the Zoom here in the chat room. I think everybody can still hear me and see me. So what I'm going to do is I'm going to go ahead and blow my screen up over here. I still have my dual monitors going, so that's pretty good. All right, and I can still see myself. All right, great. So let's get on into chapter 20, and that's a means, okay? So we've introduced the functional group in a couple other chapters before. We started with it in our last semester in chapter 7, where we're doing nucleophilic substitution, and our mean was a nucleophile, okay? And then we also got to introduce it where we used it as a nucleophile and in acyl substitutions to make amides. We've seen it in other reactions where we can actually react it with ketones and then do other reactions after that, after forming imines. And so we're going to continue on what we've introduced there and kind of formalize the entire amine system here. Let's see, are we going to, do I have to share and reshare? Yeah, let me share and reshare. There we go. Doesn't like me to pause. It'll, and chat. All right. There we go. Okay, so there we go. My screen is moving now. Okay, so the first thing we need to do is look at the formalization of the name amine, okay? So amine, as we learned on the nomenclature sheet on tracks and canvas here, is it really is a very low priority group. It's typically only changes the name of the word. It's one of the few functional groups. It's just amines and ethers are just really low on the SIT list. So if there's anything else, you have to name it as a substituent, okay? But for the systematic name, we do all of our other rules. We make sure there's no higher priority group on there, like an alcohol or a carboxylic acid. And if there is nothing else, then we get to name it for the amine, and we follow all our rules. Find the longest chain that's bonded to the nitrogen, take the E off and add the word amine. So you can have something like as simple as ethylamine or methylamine. And then as things get more and more complex, you can either use the common name, for example, the isobutylamine, or you can use the IUPAC name. For example, right here, we have the methyl, 2-methyl-1-propylamine. Come on. Are we on the right Wi-Fi? It's not showing my annotations here. Oh, I'm on the wrong Wi-Fi, that's why. All right. So let me go change Wi-Fi's here real quick. Okay, that's on the right Wi-Fi. There we go. Now we have annotation. Let's see if it writes this time. Yes, all right, great. So, so naming them is fairly straightforward. If it's as a group, you're just gonna name the whatever. So if it's just a substituent, you have the amino substituent as in our nomenclature chart. Okay, so, but the other thing about this is what we call a primary amine. Okay, a primary amine is amine with only one carbon bond. Just like we were talking with, when we talked about amides, a primary amide only had one carbon bond, and that was bonded to the carbonyl. Secondary had two carbon bonds, the carbonyl and something else, and the tertiary had three. Okay, yes, you have a hand raised.
Hey, Dr. Irvin. So I was a little bit confused about the naming conventions. I think we said it's ethylamine, but it can also be called ethanamine. It is. Which one of those do you know? Like, will we be tested over both of those?
Well, the names up above are what we call the common names, where you have just the alkyl group, and you'll know it's a common name because it'll have the YE, I mean the YL, like the methyl or the ethyl.
Yes, sir.
Signifies that it's an alkyl group, and that's a common name. When we look at the systematic names, we use the methane, drop the E and add AMINE. So that's how you can tell the difference between the systematic name, the IUPAC name, and the common name.
Gotcha, thank you.
And IUPAC names are always right. Sometimes common names will give you a little bit of trouble because like isobutyl, etc. Okay, and again, these are all primary amines, meaning that these all have a single bond from the nitrogen to a carbon, okay? So there is only one carbon bonded to the nitrogen. Let me restate that. Okay, so as we move on to more and more complex materials, we have to think about how many carbons are bonded to our nitrogen and how many hydrogens are bonded to our nitrogen, okay? So in this case here, a primary amine always has two hydrogens on it and only one carbon nitrogen bond. Okay. So when we go to secondary and tertiary amines, when we look at our systematic names, if they're the same group, it makes us easy to use like our di substitution, like a dimethyl substitution or a diethyl substitution. We can use that prefix and name it as our primary amine, okay? If we have three groups we use and they're all the same, we can use the word tri. Okay. However, if you have three different groups or two different groups, you must name them alphabetically. Okay. So again, we like with many of our other rules for naming things, we try to find our longest continuous chain bonded to the nitrogen of the amine. And so in the case of our first group here, we have an ethyl group we have a methyl group, and we have a hydrogen here. So that means our 2-carbon chain is the longest chain. So that means we have to name it for that ethyl group. So we'd say ethane, drop the E and add amine, so it'd be ethanamine, okay? But now we have to say that there's another R group on the nitrogen. And we signify that kind of like we did with the amides. I'm gonna blow it up real quick. We signify that there's a different alkyl group on the nitrogen by having that N. That capital N says that the group immediately behind that is bonded to the nitrogen, not the main chain. So in this case here, this methyl group is bonded to the nitrogen, so it's N-methyl. No, it has the YL, meaning it's a substituent, right? It's not the main chain, it is a substituent, so it's N-methyl ethanamine, okay? Now, if we have a symmetrical compound, the common name is easy because you have a di or a tri in front of the substituent name, in this case, the ethyl, and we just add the word amine at the end. However, in the systematic, one of those groups is a substituent, and one of them is naming the main chain. So in that case, our main chain, again, has the longest of 2 carbons, so we have ethane amine as our primary chain, and the other group is a substituent, and that therefore we have to have the N and whichever substituent name it is. The ethane becomes ethyl because it's a substituent, and we have it bonded to the nitrogen, so that's why we have the N there, okay? So to extend that out to tri-substituted nitrogens right here, if they're all the same, that's easy to do with our common name, because we just say it's triethylamine, because it's 3 ethyl groups on a nitrogen. However, in IUPAC, we still have to name the longest chain as our parent, and the other 2 groups are substituents, okay? So in this case here, we have N comma N, telling us that both of the ethyl groups are bonded to a nitrogen. In fact, they're bonded to the same nitrogen. If they're bonded to different nitrogens, we have a different way to do that, and we denote that with a tick mark above the nitrogens. But we're not going to name those this way until we get to biochemistry. So let's not worry about that. Okay, and again, with applying all of our rules, including the alphabetization rule and making sure we have our alkyl groups on our nitrogen here. In this case here, we have this unsymmetrical group. Our longest chain is the total of these 3 carbons here. So that's going to take our propane, turn it into propanamine right here. And then our other 2 groups are attached to it, and we put those in alphabetical order. Ethyl comes before methyl. Therefore, we have N-ethyl, N-methyl, 1-propylamine. Notice the 1 is actually the position on the carbon chain. So, in fact, we have 3 carbons, but the carbon chain is actually numbered from the nitrogen as 1, 2, 3. So this 1 is actually telling you the carbon position, and the N's are telling you where the other substituents are bonded. Okay, questions on nomenclature? So we have primary, secondary, and tertiary. We follow most of the other rules that we have there, but it is a low priority. So if you have an alcohol in there, it counts as a substituent. And you would say it's something amino, blah, 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 alcohol. So, and remember, that's on that sheet on tracks and Canvas. Okay, questions about that? Because we already talked about some of these heterocyclic and aromatic amines. We talked about them in the aromatics chapter, and we know that they have special names. Now, when they do have these special names, like the aniline or the other system, again, those are the common names. Aniline is common name, toluidine and are common names. However, again, amine is still one of the lowest substituents, so we call it benzenamine, benzamine. And then we label them by that system, where we have the other alkyl groups are denoted on having our nitrogen, right here, showing we have a methyl group on the nitrogen, but benzamine is our base. Okay. Now, and where we also learned in our aromatic chapter is that we have some nitrogen-containing heterocycles that also have different names. And the two we learned in that chapter were pyridine and pyrrole. And remember when we talked about those, they had, one of them has the lone pair contributing to the aromaticity, and the other has the lone pair not contributing to the aromaticity. Now, one thing we'll find out here in the next couple of slides is that whether or not those lone pairs are contributing to the aromaticity changes the base strength of the amine. Okay. So the aliphatic versions of these cyclic ones have different names too. A single nitrogen and a cyclohexyl type ring is called the pyridine, and a single nitrogen and a 5-membered ring is called pyrrolidine, right here. And those are very common names. You'll see them in lots of dyes and wood dyes, etc. Okay, so now we have our names, fairly systematic, easy to remember. Again, they are very low priority. They typically are, if there's only an amine on there, it's named for the amine. If there's something else on there, it's usually named for the other thing. Okay, so what brings us about amines also is we talked about that when we had hydrogen bonding available to us, it changes the boiling point of our system. When we talked about alcohols, the fact that there's such a big jump going from an ether to an alcohol was the fact that it hydrogen bonded. Okay, and when we went to a carboxylic acid, there's a big jump in boiling point because it could hydrogen bond with itself to make dimers, and therefore is increased it as significantly. However, in the case of the nitrogen, the hydrogens on nitrogen do not hydrogen bond as strong as the ones in alcohols because the electronegativity difference is less. Our nitrogen is right next to carbon on the periodic table, and therefore it's not as polar bond, and therefore it doesn't hydrogen bond as strong. So if we look at compounds of similar molecular weights that have increasing amounts of hydrogen bonding, we'll see that things like this ether here that can't hydrogen bond, all of its boiling point is taken into its mass and its van der Waals forces right here. Once we move to the amine, we get a bump up of about 40 degrees in boiling point because of the hydrogen bonding available to it from this nitrogen at the end. However, if we change that nitrogen to an oxygen, we see an even bigger jump because it hydrogen bonds stronger. Okay. Now note that it hydrogen bonds when there's a hydrogen on that nitrogen, which means only primary and secondary amines hydrogen bond. Once you take that last hydrogen off and put a new carbon bond here, it cannot itself hydrogen bond to something. Therefore, its boiling point drops, okay? So in general, your primary amines are slightly higher boiling than your secondary amines, which are higher boiling than your tertiary amines because of that change in ability to hydrogen bond. Okay. What's really nice about these amines is that most of them are completely solid in most organic solvents, regardless of how big they are, because the van der Waals forces, the aliphatic forces are the ones that are dissolving things. However, if you have fewer than 5 carbons, they can dissolve in water because of hydrogen bonding. But once you go much above 5 carbons here, they become insoluble. Okay, so now one of the things about that can hydrogen bond here is the next thing we have to think about is that nitrogen still has a lone pair on it. And that lone pair on nitrogen means it will act as a base, okay? It'll act as a Lewis base, but it'll also act as a Bronsted-Lowry base. Okay, so let's talk about the properties, the acid-base properties of the amines right here. Okay, so just like carbon, the orbitals in the nitrogen are sp3 hybridized, and the lone pair takes up one of those positions. We know this because it gives us this trigonal pyramidal structure if we look at it by spectroscopy. So we know that lone pair is taking up one of those electronic spaces, and we know that it forms that. Now, unlike carbon, which once you form 4 bonds on it, it rigidly sticks to that tetrahedral structure. In the case of the nitrogen, because it has only electrons in there and it doesn't have to move mass, we can move that electron back and forth. So we can have it in this trigonal planar and then kind of invert it like an umbrella and have the electrons pop up on the other side, which means that a tri-substituted nitrogen can't be chiral, and it can flip back and forth rapidly. Okay, it doesn't need acid or base to do this, but either one will help it. Okay. So we have that electronic and physical structure to look at it that makes it slightly different from what we see in the case of a tetrahedral carbon. Okay, so, but let's talk about that lone pair. That lone pair can accept a hydrogen, and how big or small that lone pair increases its basicity. The more lone pair character it has, the more basic it is. The less lone pair character, or if you're pulling electrons away from that hybridized orbital, it decreases its basicity. So what does that mean? It means that almost all amines act as bases. Okay. Okay. And just like with everything else on our pKa scale, the stronger the acid, the weaker the base. Okay, the conjugate base. So in the case of when we talk about amines, we want to think of it as either the base, meaning that it is not protonated, or we want to think about it as its conjugate acid. If we think about it as its conjugate acid, we can rack and stack it in that pKa scale, and we can identify whether it is a stronger or weaker base based on that scale. Okay, so if we think about it in the case of what we see here with our amine acting as a base, right here, again, the lone pair is going to reach out, form a bond with hydrogen, and then leaving the electrons on our new conjugate base right here, generating our protonated amine species, which is our conjugate acid. By comparing the pKa of our acid on the one side of the reaction and the pKa of our conjugate acid on the other side of the reaction, that'll tell us which direction the equilibrium will lie. Okay. So let's talk about things that'll affect the acidity of the basicity of a nitrogen. Okay. And these are some of the same things we saw in the effect of carboxylic acids. The inductive effect, basically, the more electron donating you have, the more electrons you're going to have in that lone pair, the more electron density you'll have in that lone pair, and it'll increase its basicity, more likely to reach out and grab a hydrogen. Okay, so electron donation means that lone pair has more electron character and therefore is more basic, more likely to grab a hydrogen. Okay, just like in the case of carboxylic acid, resonance effects are also present. If you can delocalize the lone pair on the nitrogen, it decreases basicity. The electrons spend less time on the nitrogen, therefore they don't need to reach out and grab a hydrogen, so therefore it decreases the basicity. So electron donating groups increase basicity, but resonance effects, pulling that electron density away, decreases electron density. Okay. Now, in addition to that, aromaticity can change the basicity of the nitrogen. And it has everything to do with whether the lone pair is in the aromatic, is used to make the aromatic ring aromatic, or if it's not in the aromatic ring to make it aromatic. And I'm going to show you that on the next slide. Okay. The last thing that we have is hybridization. Just like in the case of acetylene and then going to ethylene, going to alkanes, it decreased the acidity here. We see it increasing the percent of S character on that orbital decreases basicity, meaning the more likely it is to be sp3 hybridized, the more basic it's going to be. If it's sp2 hybridized, it's less basic, it has less base strength. And if it were hybridized even further to be like in a nitrile, that's even far less basic than it was as the primary or secondary amine, the tetrahedral amine. All right, so let me go ahead and remind you about where the electrons go in the case of the pyrrole and the pyridine. Remember, in the case of pyridine, we have a 6-membered ring, and the p orbital on the nitrogen that contributes to the pi cloud is not the one with the lone pair in it. Therefore, the lone pair is the one sticking out from the aromaticity, and only the single electron in the p orbital is contributing to the electron cloud, okay? That makes these more likely to reach out and grab a hydrogen. Therefore, the lone pair on this nitrogen is more basic than it would be if those electrons were used in the aromaticity. Now, when we did pyrrole, we saw that to make our ring happen, we had a 5-membered in the ring, and we had to have a p orbital in there. But to get the right number of electrons, to get those 6 electrons, we had to use 2 electrons in that p orbital, meaning the lone pair is contributing to the aromaticity. If the lone pair is contributing to the aromaticity, it doesn't need to be reaching out and grabbing out hydrogens. Therefore, it becomes less basic because the lone pair is already donated and it's delocalized in the system. Okay, so now we're looking at basically how much electron density is in that lone pair will tell you how basic or how not basic it is. The more electron density in that lone pair, the more basic. The less electron density, the less basic. Okay, so what does that mean on a scale? Okay, so I used to teach this where I would talk to you about the pKb, which is the log of the equilibrium constant for the protonation of the species. That confused people. So what I want to do is instead talk about the pKa of the conjugate acid. Okay, remember, the stronger the acid, the weaker the base. The weaker the acid, the stronger the base. So in this case here, we're going to use pKa's. And remember, increasing pKa's is decreasing acidity. Our highest, our weakest acid is alkanes at between 50 and 60 pKa. And so that makes them very, very strong bases. Okay, so if we look at the pKa of the conjugate acids of something like ammonia, ammonia has no ability for it to draw electron density away from carbon, and therefore it has a conjugate acid strength, pKa of about 9, which is below water, okay, which makes it pretty good base compared to water. It's more basic than water. Okay. If we have a little bit of aliphatic carbons attached to it, those aliphatic carbons can donate electron density to the nitrogen. Therefore, they become more basic, right? So they are less acidic as their conjugate acids, which makes them more basic. Okay. Remember, weaker acid, stronger base. Okay. Now, once we have a nitrogen in conjugation with a benzene ring, that means that benzene ring can donate even more electron density to the system or take it away. In this case, because the benzene ring wants to use all those electrons for aromatization, it actually decreases the amount of electron density on that nitrogen through hyperconjugation, and therefore these aromatic amines are more acidic because they have more lower numbers here, which makes them less basic. Okay, so aliphatic amines are more basic than aromatic amines. Okay, And then if we look at the nitrogens actually in their heterocycles, they're even less basic. They are more acidic, they are less basic. So by having these electrons go into the ring, is specifically in parole, where those electrons are being used in the aromaticity, it makes it even less basic. And the least basic amine we have is actually the one on an amide right here, because that carbonyl is pulling all the electron density it can from that nitrogen, and therefore it makes it the worst base in the series. Okay, so aliphatic amines that have carbons to donate are the most basic, followed by ammonia, followed by aryl amines, and then if our electrons are used in the aromaticity, it's really, really weak base. Okay, so if we look at it in that scale of what the conjugate acids are, we can see why the aliphatic amines are used as bases and nucleophiles in our reactions, and the aryl amines are used less and less. All right, questions on acid base right here. Okay. So I like to explain it all using the pKa scale, because then we don't have to get a different scale. Okay. All right, so now we're going to move on to synthesis. Okay, the key takeaway in these synthesis reactions is selectivity. Okay, just like before, we wanted to make one product if at all possible. It makes it easier to do. When we talked about using ammonia or amines as a nucleophile in SN2 reactions in chapter 7, we saw that if you once you reacted an amine with a nucleophile, amine as a nucleophile and displaced an alkyl halide, that nitrogen still has a lone pair on it. It can still act as a nucleophile. And then you can substitute it one more time, and if you neutralize off the acid, it still has a lone pair on it. It can still act as a nucleophile. So this thing can keep growing and reacting and reacting and reacting. So you can get a primary, a secondary, a tertiary, or the quaternary ammonium salt if you have enough alkyl halide in the system. Okay, because of that maintaining its nucleophilicity, it makes it very hard to stop. It's very hard to get a primary amine from the system. It's pretty easy to get a tertiary amine, but it's very hard to get a primary amine. So we have to look for other routes to get selectively to our primary amines. And the first selective route we want to look at is called the Gabriel synthesis, and it's at the lower end of this page here. Okay. So what we've done here is we've taken a nitrogen compound and we put 2 carbonyls on it to make a special group called an imide, I-M-I-D-E, imide. Okay, and the most common one for this is what we call phthalimide, which is made from phthalic acid, which is 2 carboxylic acids on a benzene ring. Okay, once we add those 2 carbonyl compounds, that makes the hydrogen on this nitrogen very acidic. Just imagine we were trying to make an enolate out of a carbon, and you had a carbon with a hydrogen on between 2 carbonyls. That's the most acidic hydrogen. By doing the same thing with this nitrogen here, we actually generate a fairly acidic hydrogen, and we can pull that off with just hydroxide. Once we do that, it is now negatively charged and is our nucleophile, okay? But it can only attack once. It can only attack once because of the electron withdrawing with the carbonyls, and therefore we do mono substitution on the amine here. And then just like we learned in our carboxylic acids chapter, we can hydrolyze off that carbonyl nitrogen bond, the hydrolysis of an amide, and we'll get our carboxylic acid back, and at the end of it, we also get our primary, although protonated amine. Okay. Because we only have one nitrogen site able to attack, we only get mono substitution. So this is a great route to get to a primary amine. Okay. Now, are there other ways to get to primary amines? Yes. Most of the time we get to these primary amines, we do them through reductive or rearrangement processes. Okay. So in the case of another way to reduce things, or in the case of a rearrangement here, let's talk about what we call the Hofmann rearrangement. So it starts with a primary amide. Okay. This only works with primary amides. Okay. And in the case of this, we're actually using bromine to oxidize the carbonyl carbon. Again, don't worry about the mechanism, but know the reagents. Primary, amide, bromine as our oxidizer, and then we have base. And that base starts hydrolyzing off the different bromines, and you end up making the carbonate product, a bit of sodium bromide, and our amine. Okay, now I said selectivity. Okay, notice that we are losing a carbonyl carbon out of the system. Okay, when we do this rearrangement, whatever long chain we have here, if we had a carboxylic acid that had 10 carbons on it, our amine's only going to have 9 carbons on it. We lose 1 carbon in the system. Okay, so our Hofmann rearrangement extrudes something like a carbonyl compound, and we're left with a primary amine. Okay, so selectivity, and we lose a carbon. So keep track of your carbons. That's going to be the important part. Another rearrangement we have is we can take an acyl halide and do a nucleophilic aryl substitution to get to our acyl azide, and then that thermally decomposes to give us a primary amine as well. Okay, so let's look at the Curtis rearrangement. Okay, just like in the Hofmann rearrangement, we're going to lose 1 carbon in the chain, so we need to pay attention to that. So we can start with any acyl halide and react it with an azide. Turns out nitrogen 3 minus is a really good nucleophile. And in the case of this system here, we can actually displace the chloride and give us our acyl azide right here. Now, that acyl azide actually has, like, you know, molecular nitrogen kind of tacked on here. And so by heating it, that nitrogen leaves and it rearranges our system such that it creates an isocyanate. Okay, isocyanate is just a kind of a reconfiguration of an amide, a slightly dehydrated amide. Okay, now the isocyanate is a group that when it reacts with water, it generates CO2 and a primary amine. So once we form our isocyanate in solution by just heating the system, add a little bit of water at the end, and we generate CO2 and our primary amine. Notice we've lost 1 carbon, just like in the Hofmann rearrangement, though. Okay, so in both of these rearrangements, we start with an amide or a acyl azide, do some kind of hydrolysis step to give us our primary amine and some kind of carbonyl compound. Okay, so let's see, we're doing okay on time. Let's move on to another synthesis here. We're going to start to use this azide again because this azide is a really good nucleophile, and because we know we can get rid of 2 of those nitrogens as nitrogen gas, we can use it to generate exactly the right primary amine we want. Okay, so in this case here, we're going to take our alkyl halide, and we're going to attack that alkyl halide with our azide ion to generate our intermediate, our alkyl azide. Note, these things, because they want to thermally rearrange and extrude nitrogen as fast as possible, they can be explosive with heat, especially the smaller ones. So we typically don't isolate the alkyl azide, we just use it in solution. And then the last step is we reduce off that nitrogen gas to give us a transfer with 2 hydrogens to the remaining nitrogen to give us something like lithium aluminum hydride to give us our primary amine plus nitrogen gas right here. Okay, notice in this one here, we again get a primary amine, and in this case, we keep the same number of carbons. Okay, so in those 2 rearrangements with carbonyl compounds, we lost a carbon. In this case here, we do the attack by the azide ion and then a reduction, we keep all the carbons we started with. Okay. So we have 2 rearrangements where we can lose a carbon. We have a reaction with an azide ion where we keep all the carbons we have. And the next one is we're going to make a primary amine, but we're going to add a carbon to the system. And the way we do that is with another SN2 reaction. And for our nucleophile, instead of an azide ion, we're going to use a cyano compound. So in this case, we'll use sodium cyanide. And so we have a nice anion right here on our carbon right here. So it'll displace the bromide, giving us our nitrile compound. And again, it only has adding one nitrogen to that system because it's protected as this cyano compound. And then by reducing that nitrile down, with either the hydrogen or the lithium aluminum hydride again, we generate a primary amine, but we've added one carbon, okay? So using the same starting material of butyl bromide, you can end up with the pentylamine. You can lose one by oxidizing it and getting to that. You can make the butyl by using the azide reaction with reduction, and then oxidize it, and you can lose a carbon. So selectivity in the system is the important part. There are azide and azide compounds used in airbags. There's also aminotetrazole is the other commonly one used in airbags. When you heat it to a certain point, it just generates a whole bunch of nitrogen all at once. And so that's what's used to inflate the airbag. So yes, you are correct. They are used in airbags. Okay. And if you can imagine, it's just a whole bunch of nitrogen and a little bit of heat. And then it expands and fills the bag. And that also kind of tells you why those alkyl azides are explosive, because they generate a whole bunch of gas all at once. And that's the primary part of what makes an explosion. An explosion is the pressure wave or the expanding gases. Good question. All right. Let's move on to selectivity. I'm going to go ahead and do a couple more slides here. Just like in the previous two ones where we were reducing down either the azo compound or the nitrile compound, when we get to aromatic systems, we have lots of electrophilic addition reagents where we can put nitrous on there, but we don't have a positive nitrogen that we can put back on that aromatic base. So most of the time to get aromatic amines, we need to start with a nitration first, and then we reduce it down. And we can reduce it down with a hydrogen catalyst, but the more common way to do that was to use iron and HCl, because the iron will oxidize from iron 0 to iron 3, and the acid is the one there where the hydrogens are coming from to protonate the nitrogen. Okay, so notice that hydride, like lithium aluminum hydride and stuff, those don't work very well on this. It actually reduces off the nitro compound. So we use this dissolving metal as the way to do it. Okay. So the other thing we can do, again, we've done reductions for the last three of them here. If we take a carbonyl compound like an aldehyde or a ketone and reacts it with a nitrogen compound to create an oxime or an imine, we can also reduce those down to primary amines. So in the case of this compound here, we took a hydroxyl ammonia and reacted it with our carbonyl compound and spit out water, giving us our carbon nitrogen double bond. And then by just reducing down across that carbon nitrogen double bond by adding two hydrogens to it, we can get to our primary amine. And again, this is starting with an aldehyde or ketone so that you could have a branched or a straight chain primary amine by whether or not you started with an aldehyde or a ketone. Okay, all right. So let's do one more slide, and I want to talk about the reductive amination of aldehydes and ketones. You can take any aldehyde or ketone and react it with a primary, a secondary, or ammonia, and it will generate a compound after reduction that'll give you a primary, a secondary, or a tertiary amine. Okay. So it doesn't matter whether it's an aldehyde or ketone that determines whether it's a primary, secondary, or tertiary amine. It all matters with what amine you start with. If you start with ammonia as your material, meaning it has no carbon nitrogen bonds on it, that's going to generate our first nitrogen carbon bond at the carbonyl carbon position. and we can generate a primary amine. If it's a ketone, it's a branched primary amine. If it's an aldehyde, it's a straight chain primary amine. If you already have a carbon on that amine, okay, that amine is still nucleophilic and will still attack at that carbonyl carbon. And by reducing that with a reducing agent, you will have the R group you started with on your nitrogen plus the R group that was your aldehyde or ketone, yielding your secondary amine. Okay, so this is the first synthesis we've talked about whether you can select whether you want a primary, secondary, or tertiary amine. All the other ones were primary amines at that point. Now, if you already have two R groups on here, that nitrogen is still nucleophilic. It will still attack that carbonyl carbon. And once you reduce down that carbon-nitrogen double bond, you'll end up with the primary amine. Okay. So you don't really have to know the mechanism, but I'm going to show it to you because it's basically, you know, going through this intermediate where you have your nitrogen attacking it, giving you this oxoamino compound right here. If that compound loses water, you get that intermediate amine compound. And then just by adding hydrogens across that carbon-nitrogen double bond, you generate your amine and whatever compound you have. Now, remember we had that Hoffman where we added and formed the iminium cation. That's what you'll form if you're looking at the tertiary amine. Okay. So as far as reducing agents go, we have obviously hydrogen and nickel, which was used for all the other alkenes, is very good. However, we can use these two compounds here. These are similar to sodium borohydride, which is BH4, except by adding that cyano group, it makes it a little weaker. And so we tend to use, we can use sodium borohydride, lithium aluminum hydride will work as well. But these two reagents are specifically used in these amine reductions, and they're new. We haven't used them up to now. So, but it gives you another tool in your toolbox of reducing agents. Okay, we're right at 12:50. Let me see which our next slide is and see if we want to, okay, I want to do that next. All right, so up to now, we've done selectivity with making primaries by doing reductions. In this slide, we saw we can get primary, secondary, and tertiary by choosing our amine to be selective. In the next slide, we're going to look at how to get our secondary, tertiary by using our starting material. Okay, so what I like to do now is go ahead and take our break and come back at 1 p.m. and then we can continue on with chapter 20. Okay, I'm going to go ahead and stop recording and you can ask questions.